Okay, so now that we've talked about basic antiderivatives, the idea is that we understand that antiderivatives, when we take their derivatives, we get back to the original function. Here we have a collection of some common antiderivatives. So if you have your function is just a constant k, so like the number 4, so as an example, if f of x equals just like 4, then its antiderivative, capital F of x, is 4 times x plus plus that c. So remember, c is always the constant of integration. So that one should be pretty straightforward. The rule that we kept using over and over again, I sort of think about as like the reverse power rule, because we are taking an exponent x to the n. This is when n is not equal to -1. And notice that every time we would add 1 to the exponent, and then we'd have to multiply by the reciprocal out front. So some examples, if your function was like x to the 2/3, then if we capital F, we'd add 1 to the exponent, so 2/3 plus 3/3, which is a 1, is 5/3, and then we'd have out front the reciprocal. So instead of writing this as 1 over 5/3, we would write that as 3/5. So that's the coefficient we need so that when we pull down the 5/3, it goes away, right? Because this has a coefficient of just 1 here. And again, we'd have our plus c. So we did this rule several times on the previous video. Now it does say here when n is not equal to -1. So what happens when n is -1? Right? If it's x to the -1, which we more commonly view as 1 over x, that's the special case that the antiderivative is the natural log. Okay, so we've seen it the other way. The derivative of natural log we know is 1 over x. So now we're seeing the antiderivative of 1 over x is the natural log. Notice the absolute values here. The absolute values are there because of the domain. For the domain of natural log, right? If you picture a natural log, we know that it's only true for positive values of x and not 0. So the absolute values forces x to stay within the domain. I want you to notice here that if you were, maybe I'll change the color here. So if I were trying to apply this rule, the reverse power rule, to x to the -1, I would get 1 over -1 plus 1 x to the -1 plus 1. So I'd be getting 1 over 0 x to the 0. Right, so if I try to apply that rule to this scenario when x is -1, notice that I get sort of a meaningless expression. 1 over 0 is like infinity, times x to the 0 is 1. So this is our red flag that we see. Like if you are trying to apply this rule in the case when n is -1, we get this sort of meaningless expression. So that's supposed to be your red flag, your hint, your reminder that you're actually dealing with natural log instead. Okay, so there's your hint, I guess. Okay, we have our trig functions. If the derivative of sine is positive cosine, then the antiderivative of cosine is positive sine. And then we know the derivative of cosine is negative sine, so the antiderivative of sine is going to be negative cosine. Antiderivative of e to the x is e to the x, and etc. So we have a whole list. You have in this table a bunch of antiderivatives. Now, what I'm not pointing out is cases like we did at the bottom of the previous video, is if we were doing something like, if I take sine of 2x as my function, then the antiderivative, and this is again one of the problems in the previous video, we'd have to have our -1/2 times the cosine of 2x for the antiderivative, right? So this -1/2 is there, well really the 1/2 is there, right, because the negative sign was already there, so the negative sign's there. So, but the 1/2 is there to undo this coefficient here. So what I really could say more generally is if my function was sine of kx for any constant k, then the antiderivative would be -1 over k cosine of kx. And I'm going to have to pause this video because my daughter just woke up, so we'll have a third video